This is the second lecture for Chapter 10 for Stats 253, and in this lecture we'll calculate the least squares fit for some data. In other words, we're going to calculate the slope and the y-intercept for a line. So in doing this, the first thing we did was look at the scatter plot, and we calculate the correlation coefficient to determine that the data set is really a good candidate for a linear regression, for a linear fit. And the next step will be to write the equation for that line. Now recall from algebra that a straight line is written as y equals mx plus b. M is the slope, b is the y-axis intercept. In statistics, that line is written as y equals beta 0 plus beta 1x. So that's beta, Greek letter beta, 0. Beta 0 is the equivalent of b. The beta 0 is the y-axis intercept, and beta 1 is the slope. Y is the notation changed for statistics. In the first lecture, I mentioned that if there was more than one independent variable, one would be performing multiple linear regression instead of simple linear regression. In that case, the response variable is determined by a straight line fit, so to speak, and in multiple dimensions from different x's. So you might have beta naught plus beta 1 times x being one independent variable, beta 2 times another independent variable, I'll call it z, plus beta 3 times another independent variable, I'll call w. For example, maybe you were looking at some kind of fit for politics, and x is a location with respect to Washington, D.C., perhaps, and z is the age of the person. W could be whether they were male or female. You could have one for, so you would have different factors all coming together, and let's say they're all linearly related. There's a linear correlation between y and these different variables, so you would have different slopes for each one, and that's why it's written instead of y equals mx plus b. I guess you could write y m equals m1, m2, m3, but this is typically how it's written. We're only concerned with this much of the equation, so that was just to understand why it's written like that. Let's look at a graph of some straight lines. Okay, so here's just a regular old straight line. What do you have here? Y equals mx plus b. M is the slope of the line in algebra, and beta 1 is the slope of the line in statistics. Exactly the same thing. Where it runs into the y-axis, that means the value of y when x is 0 is b. In the equation in algebra, it's beta 0 or beta naught in statistics. Now there are many lines, actually an infinite number of straight lines that could be drawn through the data points. Which one is the best? Now there's a method for finding the best line, and that's called the least squares method. Okay, in this method there are several criterion. The first one, actually there's 4. We're going to be concerned with the first 2 because those allow us to calculate the beta naught and the beta 1 for this for the line. Okay, the first one is that the sum of the residuals or errors is 0, and the second is that the sum of the squares of the residuals or errors is as small as possible. Right, I have to define residuals, and I'll do that in a minute. Mendenhall uses the term deviations instead of residuals or errors. What are these? These residuals are the vertical distances from the data point down to the line, or up to the line, depending on the case. So here's an example of 6 data points and their scatter plot and a line between them. Now, the green lines that descend from the data points down to the line for these 3, or ascend to the line here, are called the residuals or errors. Are they really errors? I don't know, but they're the residuals. They're also called the errors. I meant they are called the errors, but are they really an error in the sense of being wrong? I mean, which is right or which is wrong? The line is a model or an estimate. It is not necessarily correct, and the data points could be more correct, or they could be off due to noise or errors. So anyway, I'll put errors in parentheses, in quotes here, but the term is used. I just don't want you to think when I say they're the errors means they're wrong. Right, so now look at these distances. They're the vertical distance. There's a tendency to think, oh, how I'll find the closest, well, that's not the closest distance from the line, from the point over to the line, and not the vertical one. That's not right. The residual is a straight line distance down. What it means is that at this value of x, at x equals 1, this data point, here was the data point, and here's what the line said. At x equal 1, what's the difference? This horizontal, it says something totally different, and that's not what we're talking about. All right, so what we want here is that we want the sum. Let's look at the first requirement. The sum of the residuals is supposed to be 0. What does that mean? Let me clear the screen for a minute. Now let's look here, just for example. I could put a lot of lines through it. How about if I put this line through it? Or I could put this line through it. Why do I choose this red line? Alright, so I have to keep finding these tools. We're going to say the sum of the residual. What is the residual anyway? It would be the data point, the y of the data point, minus the y on the line. This is the residual, the equation for the residual right here. Data value, the y of the data value minus the y value on the line. And I want to add up all these, and I want to get to be 0. Okay. What that means is that the line is sort of centrally located. In the middle of all this data. This means that if you add up all of these positive differences, positive residuals, they are balanced out, so to speak, by all the negative residuals. So let's say, for example, let's say for these, the residual here is 2, let this be 2, and this is 3. This would be minus 4. This is maybe minus 2 and a minus 1. So if I add up all these, I get 7. If I add up all these, I get minus, that's supposed to be minus 1, I get minus 7. So they would sum to 0. And that's what sum of the residuals equal to 0 means. If I put that line down here, obviously the sum of the residuals would not be 0. This might be like a negative 0.5, 0, 0, and these residuals would be quite a bit bigger, and they certainly wouldn't be balanced out by the minus 5 down here. Okay. In the example that we have here, there were three data points above the line and 3 data points below the line. That is not necessary. It's not the number of data points above and below the line. It is the sum of the residuals. For example, you could have, say, let's put another data point in up here. Well, let's say I'll put a little data point here and a little data point here, and then I have, so I'd have 5 above the line. And I could put another one down here so that these are balanced out. So now I have 5 above the line and 4 below the line. That's perfectly fine. We're not looking at the number. We're looking at the residuals. Okay, so with an understanding of that, we're going to try to move towards finding values for beta 0 and beta 1 from these two requirements. So again, here's the residual. Here's the formula for the line. Remember, y hat was a line, and it's written by beta naught plus beta 1x. Okay, I'm going to substitute so I can write the residual as yi minus and the formula for the line. Hope you can see that. I have a, whoops. Here I have y hat. Here I have the expression for y hat, and I substitute that. Okay, so that gives me another way to write the residual. Now let's say that the sum of the residuals is 0. That means if I add this up, it's better equal 0. That gives me one equation. We saw it from that very simple example, but now we're writing it in general for all data sets. So here's our first requirement right here, and it gives us an equation. Right? The equation in it has these values of I. We know all those, but it's got two variables. One equation with two variables. Now let's look at the other requirement, and that was the sum of the squares of the residuals has to be 0. This is also called SSE, sum of squares. Remember that from before. And E is residuals. Where you heard that before was in the other video for the R, correlation coefficient R. It was SS, XY, remember some of the squares, but it's not really squares. And then here was SSXX, some of the squares in X, some of the squares in Y, and it was, all right. But in this case, the X's were X value minus the mean, and these Y's were Y data point minus the mean. What do we have here? We have the data point minus the line, not minus the mean. Okay, minus the value on the line. Right now we don't know what the line is. We just kind of work up an equation. So we need this, and here, but the square, we square it. So we square those and add them all up, and we want that to be as small as possible. We want this to be a minimum. Okay, again, I took the equation for the line and I substituted. So here is my second equation, and now I have two equations. Let me highlight them. The first equation is algebraic, it's equal to 0. The second equation looks like this, and my goal is to make it minimum, have a small value as possible. Alright, how do you solve this? You've got two equations, you have two unknowns. There's some hope here that you can solve this. My two unknowns are beta naught and beta 1. That's what I want. Okay, how do you find a minimum? For those of you who have had calculus, you know how to do it. You take a second derivative, or take a first derivative, set it equal to 0. That will give you a critical point. Then you take the second derivative and you find out if it's positive or negative, showing that you either have a maximum or a minimum. Well, calculus isn't required for this class, so we don't do that, and instead we just give you the results. But I want you to see where they came from. And after calculus and some algebra, we come up with expressions for the slope. Here's the slope right here, beta 1, and for the beta naught, which is your y-intercept, in terms of the data, any data set. So what do we have here? We have terms that look very similar to what we saw for the correlation coefficient, and in the next slide I will show you both formulas and you can see how they're related. Okay, I have a term data point minus its mean. I have another term y value minus the mean of the y's. Here I'm squaring them and adding them up. Here I multiply these together and add them up. Very similar to what we did before for the correlation coefficient. See what I mean by saying that once you get this notation down, it's actually pretty easy. So I think I have a consistent way of presenting these formulas and the notation in the lecture notes. But when you move off to reading other statistics books, you'll see that everybody has their own way, but I think this will give you a good grounding. Okay, so this is the slope, and now what is the y-axis intercept? It's the mean of the y values minus the slope you got from up here times the mean of the x values. So So let's look now at the similarity between beta 1 and the correlation coefficient. So here are the two expressions. Some parts of them are very similar. Here is the x, here's the x term. Okay, in the r, you take the square root of it. In the beta 1, you don't take its square root. Okay, this y appears here and nowhere else. It's just in the correlation coefficient formula. Now the numerators are exactly the same. See? Right, this makes intuitive sense. The signs of beta 1 and r have to be the same. If r is positive, that means the data is correlated in a direct manner, meaning that as x increases, y increases. And when you look at a graph of it, you see an upward slope. You have data points like this, but pretty much going in an upward direction. That will have an r that's approximately equal to 1. At least you'll have an r that's positive. What's the slope of a line through that? It has a positive slope. So the sine of beta 1 is the same as the sine of r. Of course, it's true the other way. If r is negative, that means the data points would be calculated. Let me get a different color. The data points would be going in an inverse. There would be an inverse relationship. Any line through there would have a negative slope. But when you look at the equations that way, you see once I can calculate one term, I can calculate the other very easily. Here's another important point about the least squares fit. This line is going to pass through the point made by the mean of the x values, the mean of the y values. This is not a measured point. It's not measured. But if you took the mean value of the x and the mean value of y and put a dot on the graph, this line from our linear regression exercise would go right through it. And you can see that algebraically. Here's the equation for the line in general. Y hat equals beta naught plus beta 1x. That's just the general equation. Okay. What is beta naught? The equation for beta naught is y bar minus beta 1 x bar. Okay, so I'll substitute from here for this beta naught and put it right here. Okay, so here's my equation for the line. It's the average of the y's minus beta 1 times the average of the x's plus beta 1 times the x. Now what if I evaluate this at x bar? I put x bar into this equation, what am I going to get? You can see it right away. Minus beta 1 x bar plus beta 1 x bar, because I substituted. Those are gone. It's equal to y bar. Let's see that on that graph we had earlier. Okay, here's this graph that I'm getting a lot of mileage out of. Okay, my pencil here. Okay, the average value of the x is right here, x bar. Add up all the data points, divide by however many, 6 in this case. Okay, where's the average value for y? The mean of the y is right there. If I plot x bar, y bar, I get this point right here, and here is my least squares line. It's going right through that point. Okay, now that I have this graph here, I'd like to make another point about it. I talked about it earlier in terms of the sum of the residuals must be 0. The other was the other requirement in the least squares fit method is that the sum of the squares of the residuals, so it's yi minus y hat squared, this has to be as small as possible. Alright, so the residual hasn't changed. It's still this distance here and here and here and here. Okay, but by squaring it, we get rid of the sign information. So all we're looking at is how far this is from here to here without the sign. Of course, you square it, so you kind of increase its value, but the sign is gone. What this means is that not only do you want the line to be sort of centered between all these data points, and if you have a lot of data points, there's still a lot of ways you could draw that line, but you also want it to be situated so that the distance from all the data points is minimum. Okay, you could have a nice line down here, and maybe you somehow end up with this sum of the residual 0 because you've got some outlier down here. But if you add up all these distances, it's worse than ever. It's much bigger than if you had put the line right where you did in this case. So I'm just trying to tell you some physical reasons for these two requirements in the least squares fit. Let's now do an example. Okay, here's the same use of columns. I like to do these things in columns, and this is from the same example from the text in chapter section 10.2. So again, we put all the x's in a row and find their average value, which was 3, and then we put all the y's in a row and we find the average value for y, which was what? Was that 3 also? No, it was 2. Okay. The mean for the x is 3, the mean for y is 2. Oh, I messed up my color scheme. Here's my y's. Okay, I take x and I subtract it from its mean. I'm going to need that term. I take the y and subtract it from its mean, and there we go. Now I need to square them. To find beta 1 and beta naught, you don't need this column. You don't need this column. You just need the others. But I put it there for completeness because actually I was using it to calculate r. Okay, so you take y. You've got y minus, xi minus x. You square it and add it all up, and you get this 10. And now you have to multiply these two columns. You're multiplying this column and this column together over here. You multiply those together and you add them up and you get a 7. Okay, so beta 1, here's your numerator, or yeah, right there with a 7, and the denominator right here, and you get an answer of 0.7. That's the slope of the line. For beta naught, take the mean in y, which is 2, minus 0.7, it's the slope you calculated right here, times 3, which is the mean for x, and you get minus 0.1 for your y-axis intercept. From that, you can write the equation for the line. So here's your equation for the line. Beta naught, oops, here it is, minus 0.1. And for your slope, you need the slope right here. Here's 0.7, you put your 0.7 here, you got it. That's your equation for your line. Remember that, well, you might not remember, but the correlation coefficient for this example was 0.9037. So your slope is positive at 0.7, your correlation coefficient is positive at 0.9037, and you expect that. There's something interesting about this result. Okay, so here, this was a result of compression. That was your y value versus pressure. Okay, and now we have an upward sloping line with a slope of 0.7 and a y-axis intercept of minus 0.1. So what this says, okay, and there were some data values. The data values, I think, started here at 1, something like that. Okay, these were your, between here and here, this line makes a lot of sense. These were your measured values of pressure. And here's your compression out here. So this line fit the data here. You're very sure of it here. What happens if you try to extrapolate down to zero pressure? What does this mean? -1 in compression means it's an expansion. So if you take the pressure off of it, this thing just blows up. Well, that may not be physical. Or else you set your data points wrong. So that's kind of interesting. So I just wanted to point out that right now you're predicting expansion when it's zero. So you'll have to think about that in the data. So don't take all your numbers real seriously. Always go back to your basic science and see what you're really predicting and what you really mean. Maybe the line isn't any good. You can't extrapolate with it from this data set, or it just might mean that you set your zero wrong, which I think is what happened here. Just for a check on our least squares fit, let's do the same calculation. This is the same example, and we'll look at the residuals and the sum of the residuals squared. So here's the value on the line. Now we really have our lines, and we can subtract y from the line, and that's a residual. You might not be able to see it. Let me write it up here. This is a residual, yi, your data point, minus what you would calculate from the line. This is your y hat. Value is right in this column, and you get these residuals. When you add them up, they're supposed to be 0, and they are 0. When you square and add them up, they're supposed to be at a minimum or as small as possible. There's no way to tell this without calculus, or, well, you could do it from graphing, but we don't really know that. But I did it just for completeness. But you can demonstrate that the sum of the residuals is 0.